Okay, now we're going to talk about exceptions to the octet rule. All right, couple different things, couple different exceptions. We have what are called expanded octets, odd electrons. So it has an odd number of electrons, but let's start with the one we see the most of, and that's the expanded octet. The expanded octet is when your central atom will have more than 8 electrons around it. In order for this to happen, that specific element has to be located in period 3 or higher. So nonmetals, period 3 or higher in the periodic table, they will follow the rules, general rules of the octet rule when they are not the central atom. Here we are looking at atoms that have expanded octets on the central atom. And the only reason this is possible is because of the empty d orbitals. And we will look at examples of this. Let's look at an example. All right, so here we want to draw the Lewis structure for xenon difluoride. All right, xenon. So we're going to do this like we always do it. We're going to count our valence electrons. Xenon is a noble gas, right? So it is in group 8. So how many valence electrons does it have? It has 8. Okay, so I have 8 valence electrons there. Fluorine has 7. I have 2 of them, so I have 14. Okay, so I have a total of 22 valence electrons. Here, xenon's, sorry, sometimes this messes up. Xenon is going to be my central atom. All right, and we're going to have fluorine on each side. What's going on here with my mouse? Okay, same rule is going to apply. We're going to do 8 electrons around each of our surrounding atoms. So I'm going to do 2 there, 4, 6, 8. So here I'm going to have 2, 4, 6, 8. Oops, sorry, 8. All right, so I've used 16. So I have how many left? I have 6 left. Does xenon have a full octet? It does not, so let's go ahead and fill it. It's got 2, 4, 6, 8. All right, so now I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 of my valence electrons, but I still have 2 left. So when I have the ability to have an expanded octet, I can put those last 2 here. So xenon here is going to have 2 single bonds and 3 lone pairs of electrons. Let me see if I can draw that a little bit better. Well, for some reason this is not working. Okay, so xenon's going to have a lone pair, a lone pair, a lone pair, a bond of fluorine, a bond of fluorine, and then we have the fluorine, fluoride, and then the 8 around those. So here, xenon has 10 around it rather than 8, and that's okay because it's in period 5, so it has the D subshell. Okay, let's do another one. We're going to use xenon again. All right, so it has 8 valence electrons. Fluorine has 7. 7 times 4 is 28. Okay. So 28 plus 8 is 36. So I have 36 electrons. All right, so my xenon is going to be in the middle. My fluorine are going to be on the sides. Okay, same thing. I'm going to fill my octets on the outer atoms. So 1, 2, 3, 4, 5, 6, 7, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So how many have I used now? I have used 8 around each one of them. 8 times 4 is 32. So how many do I have left? I have 4 valence electrons left. My xenon does have 8 around it, but I can go ahead and put those other 4 on the xenon. So I'm going to do it in pairs. I'm going to have 1, 2, 3, 4. So now the xenon has 2, 4, 6, 8, 10, 12 around it, and that is okay. It can do it because it's in period 3 or higher, and it can have the expanded octet. Okay. All right. I'm actually not going to have you worry about this. We're going to come back to this later. So we will come back to this later. This will not be, the bond energy stuff will not be on your exam. But next we're going to look at molecular geometry. All right, so when we look at geometry, we look at it in what we call the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. We'll just call it the VSEPR theory. And it's just basically looking at our electron groups in order to determine what the shape of our molecule is. Okay. Our molecules are three-dimensional, so it's not something we can easily draw. They have different bond angles, and the bond angles are from the outer atom to the outer atom. And so we're going to look at some of them. So here we go. So we're going to look at electron groups. The electron groups, meaning how many electron groups we have in our central atom. So here, the electron groups are our bonding groups. And this here, I have 3 electron groups here. All right. So Lewis theory predicts the number, or the Lewis structure predicts the number of valence electron pairs around the central atom. Each lone pair of electron constitutes 1 electron group on a central atom. Each bond constitutes 1 electron group on a central atom, regardless of whether it's a single, double, or triple bond. Okay, so what I mean here is when we look at electron groups, if I'm looking at the electron groups on nitrogen, every lone pair counts as 1 electron group, so that's 1. Here would be a second electron group. And this, even though it's a double bond, will be a third electron group. So the bondings count as 1 electron group, same with the lone pair. So nitrogen here will have 3 electron groups. And when we're looking at structure, we're really looking at the electron groups on our central atom. There are 5 basic arrangements of electron groups around a central atom. And these are them. We're going to go over a chart, so I'll show that to you. All right. Each of the 5 basic arrangements result in 5 different basic electron geometries. Okay. So we are going to look at the first one. Let's say we have 2 electron groups. So here is our 2 examples. This one and this one. So again, we're only focused on the central atom. Beryllium here has 2 single bonds. Each one is an electron group, so it's 2 electron groups. Carbon has 1 electron group here, the double bond, and 1 electron group here, and the other double bond. So each one of our central atoms has 2 electron groups. When I have 2 electron groups, I have what's called a linear geometry, and this is a linear electron geometry. We're going to look at a different type of geometry in chapter 6, but this would be your electron geometry. If I have 3 electron groups, here are some examples for that. Boron here has 3 bonds to it, or 3 single bonds around it, so it's 3 electron groups, and here was a picture of it. So if I have 3 electron groups, my electron geometry is trigonal planar. And there's a bond angle of 120. And again, the bond angles are always from the outer atoms, so it's 120 degrees. 4 electron groups, so here's an example. 4 electron groups around carbon. That gives us a tetrahedral geometry, and the bond angle between the surrounding atoms will be 109.5. Okay, 5 electron groups. This is when I have 5, so this is where we're going to have an expanded octet, because that'll be 10 electron groups, or 10 electrons around a central atom. Here, 2, 4, 6, 8, 10 electrons, but 5 electron groups, 5 bonds. That's going to give us what we know as a trigonal bipyramidal geometry. This one, if I look at it in a 3D version, there's 2 planes. There's what we call the axial plane, which is up and down, and then the equatorial plane, which is kind of cuts it in half. So it's like it's 2 different planes. The axial plane will have a 90-degree angle, and the equatorial plane will have a 120-degree angle. The biggest one, if I have 6 electron groups, this is where I have an octahedral geometry. And here we have, you'll see 6 bonds, so 6 electron groups. Again, here I also have an axial plane and an equatorial plane, but now in my equatorial plane I have 4 different bonds. So in all of this, the bond angle is going to be 90 degrees. Right. So let's look at the molecular geometry, or this should say, not the molecular geometry, the electron domain geometry of our nitrate ion. So we've drawn this before. I'm just going to go ahead and draw it. I'm not going to draw all this resonance structures, but it ends up being nitrogen has, and I'm not showing the lone pairs here, but nitrogen has how many electron groups? It has 3 electron groups. So we're going to look at what our geometry is for 3 electron groups, and we find that it is trigonal planar. So the electron domain geometry of this would be trigonal planar. All right. Now, this again should say determine the electron domain geometry, not the molecular. My apologies. So here I have carbon. It has 4 single bonds to chlorine. So how many electron groups does carbon have? It has 4. There's 4 single bonds. So the electron domain geometry here will be based on 4 electron groups, and those 4 electron groups will give it a tetrahedral geometry. Okay. Now, I said the electron domain geometry. Now we're going to add in secondary geometry, and that's the molecular geometry. Electron domain geometry and molecular geometry can differ. They can also be the same, but they differ in the fact that sometimes we have lone pairs, and lone pairs will affect the geometry, and I'm going to show you why. Lone pairs occupy more space. So if I have 2 atoms that are bonded together, so in here I have a pair of electrons. Those 2 atoms share that pair of electrons, and it's in a smaller bubble. If that same atom has a lone pair of electrons, it actually has more space to take up, more space that it's floating around. So it actually changes the geometry between two atoms. So let's look at, for example, our trigonal planar electron geometry, which would be 3 electron groups, right? And we saw that with our nitrate ion, right? So that gave us a trigonal planar electron geometry. Now, if I look at ammonia, actually, let me go back one. Okay. Actually, no, let's go back to ammonia. All right, so ammonia looks like this. Ammonia is NH3. Okay, that's its formula. But when I draw it, it's got 3 bonds of nitrogen, hydrogen, but then it's got this lone pair. Okay, if you were to count out the valence electrons and draw it, you get that. All right, so it has 4 electron groups. 1, 2, 3, 4. So its electron domain geometry is tetrahedral. 4 electron groups is a tetrahedral geometry. However, its molecular geometry is different. It's trigonal pyramidal. The reason being is because this lone pair takes up more space. What happens is it pushes the bond angle down a little bit. So it ends up, instead of this bond angle being 109.5, it makes it a little less because this big space just pushes those hydrogens down just a tad. So the molecular geometry for ammonia is actually trigonal pyramidal. Right. Water, let's look at water for example. This is actually a good example. Sorry about that. So water, if I draw it, looks like this. Right? It's got 2 lone pairs on the oxygen and then 2 bonds to hydrogen. These 2 lone pairs push those hydrogens down a little bit. Now, how many electron pairs does water have? It has 1, 2, 3, 4, right, on the oxygen. So its electron domain geometry is tetrahedral with 109.5 degree between them if there were no lone pairs. But the molecular geometry is what we call bent. And that's because this is going to be less than 109.5 between hydrogen and hydrogen because of these lone pairs. Again, they're taking up more space and they're pushing down our bond angle. So, and this is just a good example showing all 4 of these here, all 3 of these here have an electron domain geometry of tetrahedral. But their molecular geometries are different, and that's because of lone pairs. Like ammonia has 1 set of lone pairs. Water has 2 on that central atom. So the bond angles get smaller. All right, the same thing is true when we look at derivatives of our electron domain geometries for 5 groups and 6 groups. If I have a lone pair, it's going to affect the bond angles. If I'm talking about 5 electron groups or a trigonal bipyramidal electron geometry, if I have a lone pair, first of all, that lone pair is going to reside in the equatorial plane, and it is going to change the shape of our molecule to either seesaw, or we call it the seahorse shape. So when I have 1 lone pair, it's going to go from being trigonal bipyramidal to seesaw. Here's another way. If I have 2 lone pairs, the electron domain geometry is still going to be trigonal bipyramidal because I have 1, 2, 3, 4, 5 groups. But I have 2 lone pairs, so it's going to change my bond angles, and its molecular geometry will be T-shaped. If I have 3 lone pairs, my electron geometry, my molecular geometry will then go to linear. The derivatives of the octahedral geometry, so if I have 6 electron groups like I do here, 1, 2, 3, 4, 5, 6, its electron domain geometry is going to be octahedral, but that lone pair is going to change the molecular geometry to square pyramidal. 2 electron groups, we'll change it to square planar. And here's where you should take this and print this out. This is your saving grace. This will also be given to you for your exam. You just got to be able to draw your stuff. So let me explain to you how this works. Let's focus here on 4 electron groups. So this is like these 3 that we looked at, CH4, NH3, and water. Okay, so here the number of electron groups is 4 for all of them. Then you're going to look at your bonding groups. So here I have 4 bonding groups, right? 4 bonds. So 4 bonding groups and 0 lone pairs. In that case, our electron geometry and our molecular geometry are going to be the same. It's when I add the lone pairs when it changes. So if I look here, let's look at this one. Nitrogen has 3 bonding electron pairs, but it has 1 lone pair. So 3 and 1. It still has an electron domain geometry of tetrahedral, but its molecular geometry is now trigonal pyramidal. Here, oxygen has 2 bonding pairs, so 2 bonding pairs, 2 non-bonding pairs. So then our electron domain geometry is tetrahedral, but our molecular geometry is bent. Okay, so let's look at predicting here. So phosphorus has 5 valence electrons. Chlorine has 7. 7 times 3 is 21. So I have 26 total. So I have, phosphorus bonded to chlorine, chlorine, chlorine. Do my 8. How many have I used now? I've used 24. I have 26. I have 2. I'm going to put those 2 on the central atom. Does phosphorus have 8 now? It does. How many electron groups does it have? 1, 2, 3, 4. The electron domain geometry is going to be what for 4 electron groups? It's going to be tetrahedral. So we look at our chart. Tetrahedral. Okay. Is that also going to be our molecular geometry? I have 3 bonding pairs and 1 non-bonding pair. So the molecular geometry is going to be trigonal pyramidal. I gave you guys a bunch of practice problems on these in the same folder, so I encourage you to look at them. Okay, let's do this one. So I got chlorine attached to nitrogen to oxygen. Chlorine has 7 valence electrons, 5, 6, so 13 plus 5 is 18. Nitrogen, it's showing me nitrogen is my central atom in that order. Let's do 8 around our outer ones. Okay, so I've used 16. I have 2 left, so I'll put those 2 here. Is my nitrogen satisfied? It is not. It is lacking 2. So what I'm going to do is get rid of these 2 and put them here, make a multiple bond. So now how many electron groups is around nitrogen? 1, 2, 3. So my electron domain geometry is going to be based on 3 electron groups, which that is trigonal planar. Okay. And then our molecular geometry is going to be different because I have a lone pair here. So my molecular geometry is going to be based on 2 bonding pairs and 1 non-bonding pair. So if I look that up on my chart, the molecular geometry will be bent. Last one, all right, iodine and chlorine all have the same number of valence electrons. That's 7. So 7 times 5 is 35, plus 1 is 36. So 36 valence electrons. Iodine is probably going to be my central atom. Chlorine around it. All right, let's go ahead and fill the octets. All right, I have filled them. I have 8 times 4 is 34. Excuse me, 8 times 4 is 32. So I have how many left? 4. So I'm going to put that as 2 pairs on my iodine. Okay, so how many electron groups do we have around the central atom? We have 1, 2, 3, 4, 5, 6. So 6 electron groups gives an electron domain geometry of octahedral. But the molecular geometry is going to be different because I have lone pairs. So the molecular geometry is going to be based off of 4 bonding pairs and 2 non-bonding. So if you look at that on your chart, the molecular geometry is going to be square planar. Okay. All right. So that takes us for that at the moment. And